I will say, like I will reserve the last 5 minutes of the presentation to do that, if that's okay. So I'm going to be talking about scheduling. Yesterday I did a session in the Rust dev room. It was mostly focused at using SCHEDX to do user space scheduling in Rust. This one is more focused on scheduling for gaming, so no Rust. It's just plain C and BPF. Here's the agenda. So a few things about gaming. Gaming on Linux is becoming a serious business. Like a few years ago, we didn't have much reality for gaming on Linux. Now we have the Steam Deck, which is a big reality for gaming. We have a lot of technologies in user space that are helping to make the gaming experience on Linux more appealing and better in general. We can play any game, like AAA games in Linux devices. And also on the GPU side, we had many improvements for the drivers. So the good thing about gaming, there's a nice way to measure the performance of a game that is using the frame per second. So our eye perceives changes in light of around like 60 frames per second. That's the ideal. Well, then we are all different, of course. It may change from a person to another. But in average, if you play a game at 60 FPS, it means that your eye is kind of sampling at the same frequency. So you perceive this fluidity, like you don't see the lagging, basically. And this is like a very broad way of quantifying the gaming experience. Like if you play a game at 30 FPS, let's say, it's an acceptable play style. It's an acceptable experience, not incredibly satisfying, but still acceptable. 60 FPS is probably acceptable. 120 FPS, you go twice the sampling rate of your eye. That's probably required if you do like competitive gaming, stuff like that. But of course, this is like a generic way just to give a number, which sometimes you need to like go a little deeper on that. So for example, here's like, not sure if you can see, but there's a scheduler on the top. The same game played with two different schedulers. In the first case, this scheduler is able to achieve like an average of 67 FPS. And in the second case, it's achieving like an average of 55 FPS. So for what I said earlier, you're tempted to say, well, the first scheduler is much better because it gives you a higher average FPS. But in reality, if you try to play a game in the first case, it's really bad because sometimes you can see like down here, you're going to 30 FPS and then you jump to over 60 and then you go down to 30 again. This gives you like the impression that even the time is kind of stretching and enlarging, and you perceive like a stuttery behavior, even if the average FPS is more than 60. The second one is instead, it's not 60, but you have this experience of consistency and fluidity, and your brain would be more pleased to play a game with the second case more than the first one. So that's like, usually we call this the P99 latency or tail latency. Like you want to, that's also a nice measure to benchmark or to measure like the gaming experience. And usually the P99 latency means that you're measuring the smaller 1% of FPS across the entire run. So yeah, that's it. The average FPS gives you a measure of throughput, like how much power you can push onto playing when you're playing a game, and the P99 FPS gives you a better measure of consistency. They're both important. If you have to pick between the two, usually it's much better to prioritize consistency. Well, of course, if you go like 1 FPS, Yeah, you're probably consistent, but so usually like the best is the mix of the two. So why scheduling is so important? If like nowadays most of the work is done by the GPU, which implements like the physics, mechanics, and whatnot. But at the end, the CPU is always the manager, meaning that often like the game engine is implemented by the CPU, which drives like all the other components. State manager for the game is also implemented in the CPU. Audio processing is not implemented by the GPU. And usually games are very cyclic, very periodically. There's a main loop that waits, then it takes, receives an input as scene, and then it updates all the different objects in the scene, and maybe it passes the scene to the GPU for rendering, for example, and then it receives something back, and it sends something to the compositor, and then it goes back to the beginning. So it's like a giant loop that is constantly sleeping, and then doing a burst of activity, and then sleeping again. So if we find a way to classify these kind of tasks, and the scheduler can like boost this pattern of like being periodic and releasing, operating in short bursts and releasing the CPU often, we can probably make the gaming experience better. That's the idea. So we can see, for example, here, this is a video game, and we can see that this is a Perfetto tool. Big shout out to Google for making this tool. It's really helpful to visualize what is happening with scheduling. And as you can see here, there's this greenish, bluish little bar, the little squares here. And that's Xwayland, is the compositor, is the task that is sending to the graphic card, to the video, like every single frame. And it's operating like every 16.6 repeating milliseconds, it's doing some CPU activity, like here, very periodic. And it's not using an entire time slice, it's just using a little bit of the time slice, and then it goes back to sleep. So 16.6 is exactly 1/60, so that's the 60 FPS, right? It's operating at 60 FPS, so every 16 milliseconds it's doing something. If I try to overload the system, this is like the same game, but with a kernel build running in the background. You can see that it's still trying to go every 16 milliseconds, but it's very fragmented, meaning that sometimes it's not even able to complete like the drawing of a frame. Other times it's able, but it misses the next deadline. So that's very inconsistent. You don't get 60 FPS in this case. And that can be a problem in some cases. So why is this happening? We need to see how the Linux scheduler is working. So the idea in the Linux kernel is that we need to have one scheduler to rule them all, meaning that we don't support pluggable schedulers, or we used to not support pluggable schedulers. So why is that? For many reasons. One of them is a valid concern, like is to avoid fragmentations. If we allow pluggable schedulers, like each company is going to implement their own scheduler, and we can't join forces to have like a single good scheduler. The other reason is to avoid to add complexity to a critical component in the kernel that should be considered entirely as a hot path. But the downside of that is that we need to design a scheduler that works for everyone, so it needs to be as generic as possible. And the best thing you can do is to design a completely fair scheduler. That's the best way. That is doing like weighted bandwidth, CPU bandwidth allocation. That's the best way. You may find some solution that works really well for your use case, but if it has the potential to regress somebody else's work, it's not going to be accepted because we can't regress the scheduler. So sometimes it's like it's really difficult to upstream scheduling changes because you need to convince everyone that like this is the best for everyone. Yeah? You know, it needs to run on HPC systems, on this phone, on this laptop, servers, gaming platforms, whatever. And in addition to that, it's also difficult to conduct experiments. We have seen in the previous talk, like, you know, you need to rebuild the kernel, deploy, reboot. You may have tooling or certain scripts and whatnot that can help you to speed up this process, but it's still like you still don't have the feeling of having like an edit, compile, test workflow that you usually have with user space applications. So a consequence of that is there are some out-of-tree kernel schedulers that are maintained by outside of the mainline tree, and lots of experimental things, even if experiments are difficult, again, to conduct. So like I was saying, what the best thing you can do is to implement a generic scheduler is to implement a completely fair scheduler. And this is the equation that drives pretty much all the schedulers, at least in Linux, all the recent schedulers. It seems scary, but it's not. Meaning that, okay, forget about the integral. Let's assume the weights. W are just the weights or priorities for tasks. Basically, what you do, you can see here, you have an interval, T1 minus T0. You scale this time by the task weights divided by the sum of all the tasks in the system. Meaning if they have, like, everyone has the same weight, they would get 1 over n the amount of time. So the time is proportionally assigned to task. If there's one that has like twice the weight compared to the others, it would get twice the amount of time compared to the others. That's it. It's not complicated at all. And how Linux is implementing this, or how usually you can implement this concept of fair CPU bandwidth allocation, using something that is called vRuntime. Basically, the idea, without going too much into details, I just want to give you the intuition here. We can fix like a baseline weight that is traditionally is 100, and then we account the runtime used by each task by scaling the time interval that the task is using inversely proportional to its weight. And that's how intuitively you can see it. So this is the same formula, basically. It's just a different implementation. But I just wanted to introduce the concept of virtual runtime or vRuntime because it's how Linux scheduling works, like in pretty much all the schedulers. And basically, intuitively, you can see that in this case, if the weight of the task is really big, its time will go slower. So you account less time to the task, and it would get... I forgot to say that. You schedule the one that has the smaller vRuntime. So if the time is going slowly for a task, it would be scheduled more often than another that has a smaller weight, because it would get, its accounted time will be bigger than the others. Basically, that's the idea. And you can play with priorities when you set the nice of a task. This is what happens under the hood. This is how the CFS scheduler was implemented, the completely fair scheduler, this one, before 6.6. Now we have EVDF, and EVDF is the same. It's still based on vRuntime, but it's a deadline-based scheduler. Now, without going too much into details, the deadline is determined as the vRuntime here, plus a scaled amount of time that the task is requesting. So let's say if a task is requesting a small amount of time, like the Wayland that we have seen earlier, it would get a shorter deadline. Therefore, it would get more chances to be scheduled. If a task is requesting a lot of time, like a bigger time slice, it would get a deadline that is bigger, so it will get less chances to be scheduled. In addition to that, because this is how deadline is implemented. And this is how you prioritize more latency. The whole motivation about eVDF is to be better for latency. There's also the concept of lag, which is like the, this is not the definition that is in the paper, but it's more understandable intuitively. Basically, it's the difference between the ideal time and the actual time that a task got. And the lag determines the eligibility, meaning that you can schedule a task only if it has a lag greater than 0, meaning that you can schedule a task only if it got less time than the ideal time that it should have gotten. And it's a way to enforce fairness more. And this is actually hurting performance in terms of latency, but it's a good compromise to still be completely fair, like CFS, so we don't regress, for example, server workload. It's still a completely fair scheduler and generic enough. But at the same time, we can allow tasks that are requesting run shorter time slices to go more often. So it's a trade-off. It's a little compromise. We prioritize latency more, but at the same time, we still enforce fairness. So there are improvements in terms of latency and gaming, but it's still not ideal. And it's not ideal because we need to enforce fairness, because the scheduler is just one, and it needs to be fair. So here comes SCHEDX. SCHEDX is a new technology in the Linux kernel that allows you to implement different scheduling policies as BPF programs. I'm not going too much into details on this because we don't have much time. This is about scheduling and gaming. But basically, you can write a program as a BPF program, load that dynamically in the kernel, and this program would replace the actual in-kernel scheduler at runtime. You don't have to reboot. You just when you have done your experiments, you Control-C your program, and all the tasks will be moved back into the default scheduler. Of course, the major benefit is rapid experimentation. It's safe because BPF is like, your BPF program runs inside something like a sandbox environment, so you can't crash the kernel. And you're forced to use GPL-v2. You can only load GPL-v2 BPF schedulers. Otherwise, there's a verifier, there's in-kernel verifier that would reject your scheduler if it's not GPL-v2. So the idea is that we can use SCHEDX to relax the fairness constraint here and implement our own scheduler, which is more aggressive. Because sometimes, we don't really care about fairness. If it's not fair, whatever. So we can use this idea to design a scheduler that is more suitable for gaming, for example. And so these are a few things that seems to work really well for gaming. Of course, detecting latency-sensitive tasks is the key. And over-prioritizing these tasks, paying the fairness constraint is actually a winning situation for this use case. So, the idea is to detect, for example, when tasks are often releasing the CPU, like detecting the voluntary context switches. Those that have high rate of voluntary context switches can be prioritized more, and in this way you get the task simply gets more chances to run the task that you care. If you have, in presence of background noise, other tasks running in the system. There are other techniques like tracking the sleep wake-up frequency, because that's the same thing that you get in the user workflow when there's the main thread loop that waits for the scene, it updates the scene, sends the scene to the compositor and whatnot. And if you have a lot of tasks running in the system, it might be a good idea also to scale the time slice that you assign to each task, but by in a way inversely proportional to the amount of tasks that are running in the system. So this thing seems, according to our experiments, these strategies seem to work really well for gaming. So this is an idea that we came up with. It's just an example. We tested. There are many different schedulers in the SCX repo, in the SCHEDX repository. This is one of them. And it's similar to EVDF, but there's not the eligibility constraint. Like every task we just use the deadline. And the deadline is determined by the VRAM time, so there's still a little bit of fairness, like the scheduler is not completely unfair. There's still some fairness, and this is the VRAM time, VT, and there's also a delta V, T. This is basically the amount of time from when the task becomes runnable. So let's say you have a wake up, for example, until the time when the task voluntarily releases the CPU. So if you have a latency-sensitive task which operates in small CPU bursts and then it goes back to sleep, the second element here will be really short. And then you have the VRAM time that gives you fairness. So the two combined together, you can see, right, that the deadline becomes shorter if the second part is really small. So a task that has used less amount of time slice before would get a shorter deadline. Therefore, it will run more often than other tasks that have used like the whole time slice, because they would get a deadline like bigger like this. Is it fair? No, but who cares? And yeah, let's show that there's a demo. I don't know if it works. Whoa, okay. So this is, I'm playing like, can you see that? Or maybe here is better. So I'm building the kernel while playing Counter-Strike. And amazing, yeah, right? Amazing performance, 4 FPS. This is way below the acceptable range. So I'm starting a scheduler, BPF land is a scheduler at runtime. Then I die because I'm bad at this game. But anyway, now I'm going 30 FPS, which is not great, but still, you know, it's still better than going 4 FPS. And I'm building the kernel in background with make-j32. So this is Baldur's Gate 3, another AAA game. 60 FPS without doing anything, of course. Now I build the kernel again, and with EVDF I go to 30 FPS, which is acceptable. But I'm in the character creator menu, so it's okay, whatever. Then I start BPF land, and now I'm like 60 FPS solid. Like, and if you plot the graph about P99, it's like super consistent. So this is Cyberpunk. By the way, big kudos to the Cyberpunk developers. This is going 20 FPS, but I can barely notice that. I don't know, they do some black magic too. So even if the FPS is crappy, but the game is still fluid. But again, I run the kernel build, and with BPF land, it's going 60 FPS again. So BPF land. But anyway, the thing is like, so BPF is just using this algorithm, which, so one question could be like, why don't you upstream this and you replace the in-kernel scheduler? Because that would be a terrible idea. BPF land is great for this particular workload. It's not great in general. It's great to prioritize latency sensitive, to over-prioritize latency sensitive works. And so, but the good thing about SCADX is that you can load schedulers depending on your particular use case. And in this case, it seems to work, and it's just this algorithm right here. So, conclusion. Can SCADX help gaming only? So this was a very extreme situation, right? Building the kernel while gaming. I mean, if you do that, you deserve to get 4 FPS. Like, why are you doing that? But jokes aside, so you need to look at the bigger picture. Like this is the idea to minimize the P99 latency. You may have a system that runs the game, but there are other things running in the background. Let's say an update is started in the background. If you're alone and you're playing video game in your room and there's an update and you lose some frames, whatever, but there are other scenarios, let's say competitive esports, for example, competitive gaming, being able to minimize the impact of potential OS noise or background noise can be relevant. there's also the fact about, project this into a totally different scenario where you have latency-sensitive workload and CPU-intensive workload. That's the same. Like, it's a game, but you can map a similar scenario and have cases where you want to prioritize latency over throughput, and you have both workloads at the same time running in the system. There's also the fact that many other factors are involved nowadays in gaming platforms, but in systems in general, like topology complexity, power saving, energy efficiency, whatever, and different kind of workloads. So being able to have a technology that allows you to, switch between different schedulers can be interesting. And yeah, scheduling specialization could be the key to get a better gaming experience or better experience with specific workloads. Okay, how much time do we have? 10 minutes. 10 minutes, okay. I would say let's do the 5 minutes, the giveaway. Where's Johannes? There you go. Okay, Johannes have the prize. So we have 2 winners. Oh, let's see if I can show. Oh gosh. So we got 2. So we got 2 submissions. One called Weird Prior Scheduling. I love the name. The other one is okay. I can describe the other one. Let's go. So we have 2. Okay. This one wins. Himadri, where's Himadri? Okay, you win. So that. No. So the idea was to show that, like, it's a technology that it makes really accessible to do scheduling. I love the second pull request because the scriptures. So I don't know if you guys know if you know them. Michael, is it? Are they here? No, whatever. If you know them, tell them to come and get a T-shirt. But I love the description that says, like, not sure if it makes sense. Okay, no, but in the commit, they say, I don't have any experience with scheduling, but I came up with this idea. And it actually works. Like, it's a working scheduler. So this is like a scheduler with 2 priority queues, one for the kernel threads and another for the regular tasks, which is a cool idea. We like that, so we would like to give a T-shirt. The other one is the one submitted by Madri. So this is actually a cool idea. I think we should implement this, like, in production for real. The idea is to use the CPU max concurrency. Is Mathieu here? Mathieu? Where's Mathieu? I saw Mathieu. Whatever. Well, that CPU max concurrency allows you to set the concurrency level per C group. So the idea was to pass this concurrency value from the host into the guest, and the guest would run a SCADX scheduler to match the concurrency level and basically dynamically scale the vCPUs without actually scaling the vCPUs. So it's a fast way to adjusting the CPUs used by a guest by passing this information in the kernel, which is I think it's a cool idea. So, yeah, you can give her. Yeah, and thanks for submitting the ideas. Questions?
Thank you for the talk. Oh, okay. Thank you for the talk. I thought, did you also, it's great, right? But did you also think about pinning to a certain core, basically? So pinning as task to a certain core, so it constantly hops otherwise at my system, and it loses the CPU cache internal.
Yeah, so core pinning is a good idea for cache locality.
Yeah.
Actually found, so it's interesting because in some games we found that the opposite is actually better.
Okay.
And because, you know, the Linux scheduler uses a run queue per CPU, and it has, or per scheduling entity, let's say. And there's a load balancer that determines like when a queue becomes too overloaded, it migrates tasks. We try to, most of the schedulers that we have in SCHEDX, they just use a single run queue to, and then they spread tasks around the available CPUs. Of course, this provides a better core utilization, so it's more work conserving, with the downside of degrading the cache locality benefits because you are spreading the tasks around. This works really well, for example, in builders. If you do a parallel kernel builder, you can save a few seconds, like well, let's say a few seconds over a small kernel build. So if your kernel build takes 5 minutes, you would save like 5 seconds, let's say. In games, with some games, like for example, Counter-Strike, this is not a good strategy, but yours is better. So pinning tasks. Other games,
especially when you have lots. Yeah, today more and more processors have a lot of core counts.
Oh yeah, exactly.
Camera can see you if you go past the line. Yes.
But good question. Yeah.
The schedulers you're proposing and trying, isn't that just a fancy way of bypassing a real-time system, and the kernel real-time extensions now have been permanently streamlined, so isn't that the go-to solution?
Yeah, so real-time is, that's interesting. Like you can use the real-time or the sched-rt class to say, okay, I have something that is really critical. I just assign the task to the real-time sched class, and it will always win over everything else, which is acceptable in some cases, but like this doesn't scale really well. For instance, if you have just a single task or a few subset of tasks that you can move and promote to the sched-rt class, that works. But like there are systems, for example, VR headsets, let's say. They have the game, they have telemetry, they have cameras, they have audio. You start to, sum up tasks that each one thinks that, oh, I'm the most important in the system, therefore I need to be real time. Oh, I'm also important, so I need to be real time. So at some point you don't scale. And so there are cases where you need a more generic and systematic approach, where you can model, like for example, this thing is more effective, let's say, and you don't have to do anything.
Hi, thanks for the talk. I'm curious, and it might seem like a very weird use case, but I could see myself running a build in the background using half my cores while gaming. So I'm curious, what was the performance change regarding the build? Like you were compiling the Linux kernel. How much time extra did that cost while you were gaming? Is it actually a feasible strategy, or would I need to wait 10x the time to actually run a build?
No, it's actually interesting because, yes, of course the kernel build is going to take longer, but not that long because coincidentally what you're doing, you're also prioritizing those tasks during the build that have latency requirements. And sometimes, like, let's say you have a short compilation unit that would immediately release the CPU. You end up prioritizing that, and it's not affecting the game that much. Maybe you lose like 1 FPS, but that's fine because you're also modeling the tasks that are not the game, but for a coincidence, they end up being using the latency-sensitive pattern because they're short. So let's say if I have to do an average estimate, your kernel build time would be, let's say, 20% slower, but your game is like if you see, like, you go from 4 FPS to 30 or from 30 to 60. So your games is 2 times faster. Let's say if faster is not the right term, but whatever. Your game is twice as fast as normally, and your kernel build is like 20% slower. So it's still a trade-off, but not bad.
All right, we're out of time. Thank you very much.